I will talk about a little bit about how sampling weights of neural networks, mostly it will be in just normal fully connected neural networks. We will touch upon CNNs at the end, but it's certainly an open question still. So it will be more about the ideas, not about any concrete results. So we will, and this will also be in more of the sense of extreme learning machines, for those of you who have heard of that, not in the terms of like Bayesian sampling or these kind of things. So more in the random feature methods scheme. Okay, so let's just introduce a little bit here about random networks and extreme learning machines. Obviously, I assume everyone knows a little bit about neural networks and the standard backpropagation, which of course works terribly well, but obviously so slow. And at least for me, that works more in the theory part. It's certainly much harder to like show results for and to analyze. In particular, like compared to like, for example, random networks, you don't really have this sort of what I would call like this probability bounds. So, and what I mean by that is basically that if you can add some probability terms to your bounds, such that when the probability goes to 1, the bound goes to infinity, it is definitely much more easier to work with. You could maybe introduce something like this in stochastic, but it's gradient descent, but it's yeah, not very clear at all. While in this extreme learning machines scheme, we definitely have this already from like early 2000s results on this for like Gaussian distributions. Yeah. So if you think of a neural network where you sample the weights of the hidden layer. So if you have like one hidden layer, you sample the weights of the hidden layer, the weights from the Gaussian, and maybe the bias just from uniform between -1 and 1. And then we solve for like the outer weights. So the W2s here are the outer weights, and then some bias as well we had here. Now solving for this while holding the other weights fixed, so the parameters inside the neuron fixed, obviously makes it a much easier problem. So for example, if you have a least square loss, it becomes just a least square problem, right, to minimize. And we have both a lot of more strong results on this in terms of theory, but also we also know that it works pretty well in practice. So sample these parameters definitely makes it more efficient as well, because backpropagation can be heavy. In particular, if you go deep, right now we're just working in one layer, but we will also go deep. And yeah, while it's efficient, this also like obviously gives us a lot more analysis tools, as I just said, with the probability incorporated in the bounds. However, there's a few problems with this, of course. Like obviously, we see in practice that they don't perform as well as, like, for example, using Adam or any of these standard optimizers. And one of the reasons behind this, obviously there are many. Obviously, once you're sampling, it's a little bit about just redundancies. You have to probably have more neurons. But this shouldn't technically be that much of a problem if it's also much more efficient to train. But the other problem is basically if you think of having an input space that is low dimensional, but in a high dimensional ambient space, the problem then becomes that you're sampling from this ambient space, because we don't know what the input space is. So we will still work in this capital D dimensional space, but if the input space is a lower dimensional space, so it might be a lower dimensional manifold, right? Then you're sampling a lot of redundancies and a lot of things that are even orthogonal to like your input space. So that's not great. And the reason probably why it works still in one hidden layer for some problems is obviously that you have the dimension is quite accurate, so to the ambient space, so you don't deal with these problems. And why it then struggles with, if you go deep, if you just sample all the weights of all the neurons in a deep network, what you'll then encounter is that you typically have a lot more neurons than the dimension of your input space. So you just enforce the same problem really, because then if say you go from having N1 neurons in your first in layer, and then you're going to sample weights for the next layer. Well, if N1 is much greater than D, the image, so if you take the input space and put through the image of the first in layer, it is a low dimensional in a very high dimensional ambient space, with the dimension of the ambient space being N1. And you're still sampling there, so you still get this redundancy, and it becomes just much worse when you go deep for that reason. So before I go into like the details here, just to set some notation for like the input space, we're going to have some input space X, fully connected neural network with this phi and some parameters, these matrices and vectors, W and B. We will have L layers, where L is the number of hidden layers, so it's not including the last layer, so the output layer. And the number of neurons is NL in layer L. You will also look at for each layer, so we'll say that phi of L of X is basically the image passing through the first L layers, with like just phi of 0 being the identity. And we will also work with individual neurons, of course, on weight, with weights and bias, and we just notate them like this. Okay, so instead now of looking at this only sample from like whatever the ambient space is, why don't we consider the more using the more information we get from the parameter space itself? Sorry, from the input space itself. So obviously there's already many sort of hidden implications in like once you use your data, you will obviously have used your data to inform your parameter space. So if you use gradient optimizer, you do this posterior distributions in Bayesian sample, obviously conditional data. There's also been a lot of theoretical work on like connecting parameter space and the input space in a not as direct way as we will do today. So for example, Speck and his collaborators show some great results on the duality between parameter space and input space, and show that they form a reproducing kernel Banach space. So the idea we build on is based on Galaris and his collaborators, what he did was basically trying to perform some numerical analysis on PDEs using one hidden layered neural networks. There's like several schemes he uses, several different ways, and like some assumptions on low dimensionality of the input space, so a low dimensional manifold basically. But the key things that we're gonna pick from this paper is that the way he forms sample the weights inside the hidden layer is basically by sampling uniformly between 2 points from the input space, and then he construct the weights by taking the difference and then setting the bias as the inner product between W and X1. So if you think of this in terms of ReLU, and remember that in our notation we subtract the bias. This means that if you put input X1 now as an input to the neuron, it will map to 0. This worked well for the shallow networks and for the particular problems they worked with, but we also wanted obviously to look into like both extending the idea to any form of problem that you typically use neural networks to. So both in regression and classification setting, they used only ReLU. We would also, of course, like to also see other activation functions and if they work as well in those, as well as we would like to see if this also works in when going deep, where really the problem shows in like the normal extreme learning machines setting. When you go deep, it's really where the problem occurs. So, and in addition to this, we'd also like to perform analysis on the space of networks, which is sort of what I've been doing. So we tweaked a little bit on the ideas of Galaris. So in the rest of this presentation, all the weights will be on this form here. It will be some constant S1 times this difference between 2 points, and then divided by the square of the norm. Importantly, with the square, we'll come back to that, but yeah. And the bias is pretty much the same as scalaris, but we also add some additional constant here. Now, we will work with two activation functions that really encapsulates the two very large branches of activation functions. You have ReLU and all of its sort of variants, and then you have tanh, and obviously sigmoid is quite similar to this. For ReLU, we're basically going to do as scalaris. We're going to put S1 to 1 and S2 to 0, so we don't add anything, and the only difference is that we square the norm. For tanh, we're going to do a little bit different. We're going to take the term here will be 2 times this other, the S2 terms, and the S2 term will be natural log of 3 divided by 2. And we will see why that is the case. So the idea is basically we want to, in the ReLU case, we want to sort of use it more in the regression case, and therefore we will like to really get the values correctly between 2 points, right? So we would like to interpolate between 2 points. That is the idea. So if you take a lot of points on your input space, and you take this and sort of interpolate linearly between points that are very close to each other, and then hopefully by basically choosing arbitrary, or like basically training the linear layer at the end, hopefully that will be able to perform well. While in tanh, we are thinking more of the intuition, at least, is more in the realm of classification, and there we would like to have x1, for example, being from one class and x2 being from the other one. And then we basically, little bit arbitrary, we chose that they should be at least mapped to, both are mapped to the same, just with this different sign. And it's basically 0.5 and negative 0.5. So that is where the natural log of 3 over 2 comes from. Obviously, you could choose any value, but yeah, we want something in between, basically. And importantly, it goes through 0 in the exact midpoint between x1 and x2. So just to like give like properly intuition behind it, if you think of having like this input space here, and you have this boundary, this line that goes downwards here, this is the classification boundary. You basically want to find a lot of points that are close to the boundary, 1 point from each class, and then create tanh between them. So then you see that you will typically have positive values in the on one side of the classification boundary and negative on the other one, and then 0. Like obviously this is a dream situation where you have 0 exactly on the classification boundary. This is not what happens in practice, of course, but yeah, that's the intuition behind it. So, but what about deep networks then? As I said, we would like to also see if this can work in deep networks. So it's a little bit the same in terms of what you do. It's just that you have to now construct or sample layer by layer. Now, obviously, this isn't like a huge deal in terms of computational speed, because number of layers are like not a real issue when training networks with this sampling scheme. Like whether you can sample them at the same time or just sequentially doesn't really affect the computational speed much. It's not a bottleneck to say. So if we have now sampled L-1 layers in the way we already saw, then it's basically constructing the weights and bias of the next hidden layer is basically just by putting them through the L-1. So you still sample 2 points from the input space, and then you just pass them through the already sampled network. So it's pretty much exact same, except for that the space that we construct the weights from are from this L-1 layered space instead. So the output of L-1 layers space instead. So the sampling dimension obviously still follows the dimension of the image and not the ambient space itself. So even if you go deep and you probably want more neurons in your layers, in your hidden layers when you go deep. You still carry the information from the input space, which is like what is key to making this work. So even though NL might be large and you have a large ambient space, our sampling space is still sort of in a carry the same dimensionality information that the input space gives us. Now we consider still the sampling space to be x times x, but you could also argue about the image of this and then maybe make some push forward measure. This is possible. It is a little bit more tricky, and it's definitely much more details when you start introducing probability distributions over this. It's much easier because you have to create distributions that are obviously valid probability distributions, and this is not straightforward when you start going deep, because if you consider sampling space to be this image space instead, then it changes depending on what you did previously, and then there's a lot of weird situations that can occur. So it is easier, at least in our view, it is easier to work with still x times x for each layer as the sampling space, and then just pushing them through when you construct the weights. Okay, so we have now obviously shrunk the space of weights and bias that you can take. We no longer can take things in RD. For example, in the first in layer, we're restricted to whatever dimension the input space is, and whatever dimension, and further when you go too deep. How does this affect the space of networks? Here we have to be a little bit careful. Like typically when you start looking into theory in neural networks, a lot of times you can just assume that you're working on a cube in 0, 1, right? Cube. And then you can just scale it because the weight space is not dependent on this. But since we depend on the input space, it would be very restrictive to just assume that it's a cube all the time. But we still need some assumptions, because there are obviously input spaces that will not work, and we will come back to this. And yeah, so basically trying to find some necessary assumptions. This is definitely not a necessary assumption. This is what we found as reasonable enough. So if you consider this space here as a non-empty compact subset of RD, and then we include this reach, and reach, you could think of it as just saying, okay, what is the maximum length such that all the points in this reach has a unique projection down to this original X prime space. We could of course do it differently, but the reason why we choose to use this reach is that if we don't include any points outside of this reach, we still have this, we still sort of contain the structure of the manifold or whatever we're working with at the moment. So we still contain the information. If you add too much noise, it just becomes, at the end you could say that we could add noise such that you almost get to a cube, right? That would be possible, but again, too restrictive. We just assume that the input space is now this, where all the points, you choose some noise level that has to be less than the minimum of the reach, or 1. This will be the input space we're working with when we present the next theory. So the first theory is just the universal approximation theorem. The space of all sample networks with one hidden layer is dense in the space of continuous functions. And the really key idea here is that the proof, in particular when using Rayleigh, the proof is very constructive in the sense that we just assume that we have an arbitrary neural network with arbitrary weights and bias, and then we basically translate from this to a network that follows, that basically uses points from the input space to construct the weights. This means that a lot of the theory that is already available for like normal neural networks also follows to R pretty straightforward, not just the universal approximation theorem. So just to give you a little bit of like hint of why it's not obvious necessarily is looking at the bias and how you can translate from the bias to the way from an arbitrary bias to R type of bias. So assume that you already fixed your W, so obviously fixed your neuron in weight in your neuron, and then consider this space here where we have an input space which is not connected. You have two paths here, and then we just use the W to project it down to R, and we get this. We get some values. There are green lines here. Says these are the values that comes from the first part, and this is the second one from the second part. And if the bias was in one of these parts, you would just pick a corresponding x1 and then figure out what x2 has to be to construct the correct weight. That would be fine. If it's outside but behind all of this, then it's also fine, because then you could just pick the bias to be at the end here, and then add all the additional constants that will be added to the whole space. You can just add that bias at the end in the linear layer, because those are arbitrary, as remember. If it's in front here, it's also no problem, because then everything will be set to 0, so you can just pick your bias at the end and find a corresponding point that makes the bias become here as well. Now, if the bias is in between here, that's a little bit more tricky, because you could, of course, pick the bias to be here. So this part here will then be set correctly to 0, but you still have an additional constant that should just be added to a certain part of the input space. And this is why, if you actually look at the paper, the results are, yes, constructive, but if you don't assume anything more on the input space than what we've done already, then you you might have to have 6 times the number of neurons that you would have in any original neural network that you start with. So it only holds up to like a 6 times factor, basically. And the reason I don't assume you will understand this, it's quite messy. It's just a construction of, you can see that we have 6 neurons here. These are possible to create with R types of just picking points correctly, basically. And if you sum up all of these, you get this function here, where you have 0 on this part, and then you have this here, which corresponds to this space here, right, where nothing is mapped to, so we don't care what happens here anyway, but you will have this rise here, and then you have a constant from here, an output. So you add constant only to a certain part of the input space. So that's just part of the proof. I just want to show you that it is constructed, but it doesn't have one-to-one on the number of neurons, unless you have, for example, a connected space, then it's exactly the same. Okay, so I told you that the proof is quite constructive, which means also that we can start using it in different theories, right? So if you look at, for example, the Bayesian space, which is functions on this form here, with this one probability measure on the parameter space that one chooses, where the Bayesian norm is finite, and the Bayesian norm is basically just looking over all possible probability distributions, such that f of x, such that the corresponding function, if you plug in whatever mu here is into here, you will get the same function as the one you actually picked. And then basically looking at just having some bounds on the parameters in that space. And this is obviously corresponding to the work from Bayesian and was developed by Wine and E, among others. So the theorem then becomes that we're now working in a cube. Actually, you can definitely extend it, but just to show that things falls quite quickly. If you are in a cube and you have an f in the Bayesian space, then for any number of neurons in the shallow network, and any arbitrary probability measure, there exists a sample network phi with one hidden layer, the exact same number of neurons, because we're in a connected space, and real activation functions such that this bounds here holds. Now this epsilon here is not dependent on n1 at all. It is basically just something we have to add, because we cannot, if the x1 point technically has to be on the border and the x2 point has to be outside of the space, if that is technically the correct pair we want, then we have to move it inside, of course, because we cannot sample something outside of the space. And then you can do this with arbitrary accuracy, basically. Now extending it to, like, for example, non-connected spaces, you would definitely get like 6 times the number of neurons, but the results will probably still hold. So now we're thinking of more of like 10H, because that's sort of another sort of class of activation functions really that we want to use, and we found in practice to be quite useful in the classification setting. So, and just to like pinpoint why we have this square of the norm, it wouldn't work if you just if you either divided just by norm or didn't do anything, like the one they did in Galaris. This part here would not work, because what happens when we do this is that we add a positive constant, and the positive constant is bounded below. That's fine, but the key part is as long as you can get x2 and x1 to be as close as possible, you have this unbounded constant here, which is inside a neuron. Now this wasn't a problem for ReLU because ReLU is positive homogeneous, but here it's really key. Otherwise, yeah, we would be limited in a number of functions that we could approximate. Now we just go ahead and prove it really simply. It's not as constructive proof because we use arbitrary many 10H neurons to approximate one ReLU neuron, where the ReLU neuron has the weight and bias on the correct form, or R form, with the 2 points. And the intuition is quite simple then. Going from there, it's having some ReLU and just adding a function, stepping function, and adding a lot of 10H functions and just summing them up. Basically, all of this can be done in a neural network, one hidden layer neural network, and if you add more of these steppings, right? So if you add more steps, you would have to add more 10Hs, but it all has to be, they have to also have sort of a steeper incline, and this can be done because you can choose points arbitrarily close here, which follows from the assumptions we have on the input space. Okay, but what about deep networks? Again, because if you think about it, you can definitely screw up, right? You can definitely construct weights with points such that the space of points that you can pick in the L minus, when you construct in the Lth layer, right, where L is greater than 1, it's just, yeah, it's completely, it's just really, really bad, right? You don't have any really points that you could make any good networks of. That can definitely happen, right? So our question is, can we at least guarantee that there are networks, deep networks, that still can fulfill this universal approximation? So we're not working with narrow deep networks. We're just thinking of, okay, if we allow arbitrary neurons, but we go deep, will that ultimately just be bad, or is it possible, right? And it is possible. I think just for time's sake, I will skip a little bit of here, but we do have the same, at least for ReLU, we do have the same result with denseness for any L, basically, so any number of hidden layers. And it's basically just trying to, we just show that you can at least construct the L minus 1 layers, so capital L minus 1 layers, such that you contain the information from the input space, enough information such that when you then pick the weights of the last hidden layer, you can basically use the results from our previous slides. Okay, but now we talked about mostly about constructing networks. We obviously want to sample them. And since we now have turned from sampling just randomly in this ambient space to actually sampling from the product space of x sub x, right? We could, of course, start with just using uniform, which is what Galaris did in his paper. However, we have a lot of information about x. We both have information about like where they are distanced in the input space itself, but we also have information about the output space if we're in like a supervised setting. So if we add some restrictions that we have some Lipschitz continuous function f, access to be compact, So we're not working with the noisy input space that we talked about. We're just thinking of a compact space, and that this has a finite Lebesgue measure, but also non-zero Lebesgue measure. We can sample by constructing densities layer by layer, so having conditional densities, and then just the full distribution will just be the product of this, these conditional, sampling layer by layer, thinking of having some weights and bias for the previous layers, L-1. We condition on these, which is basically like conditioning on the axis itself, right? This is just a slight abuse of notation. And then looking at the 2 points from the input space, so this is from the original input space, we construct this density here, which is basically looking at the difference between the output, the true output, and the difference in the image. So once you put these points inside the already constructed L-1 first layers, you get these points here, and we look at the difference there, so in this image space instead. And we have some regularization, but which we put to 0 when L is equal to 1. So when we sample for the first layer, we don't add this epsilon, and further when we go deep, we add this small epsilon. And what is this basically saying is that if you think about it, you want to have points, and you want to sample points that are changing a lot around in the output space. So they seem to be quite different. That's one thing. You can almost think of having like a high gradient, right, if they're close enough. But you also want to penalize picking points too far apart. So the intuition behind, like, for example, in the classification setting, it was picking points close. And this is also for the Rayleigh, right? You want to have like some linear interpolation between points that are very close to each other. And also, if you also think, of course, like for any manifold, picking 2 points and then taking the difference, it would be very bad, right? Because if you have like a U-shaped manifold or something like this, picking 2 points and the difference, it will be go across. It's probably not what you want. You will probably want along the input space, because that's where the function changes in the meaningful way. That's what we care about when we approximate. So sample where it matters is basically looking, if you look, for example, in a classification problem where like we have a class A as the white one and class B as the black part, then if you sample and show the density just uniform, which we'll also use in the Galari's paper, you obviously just get points arbitrary, right? But in our sampling density, you see that we definitely get a lot around where we would like to sample, right? We would like to sample close to the border. But we would also like to sample where the classes are different. Now, choosing all of this also gives us some nice equivariance invariance results quite quickly. So if you think of having H as like a scalar and rigid body transformation, or Euclidean transformation is also called sometimes, and also add this assumption that there exists another transformation in the output space of a scalar and rigid body transformation, such that this occurs. Then if we have two sample networks, one from the original space and one from the transformed space, the following holds is that if you sample, if your points that you sample in the first in layer are the same, just transformed, the output of the first in layer is the same. So this comes just from basically that suddenly you have points in all of the parts of the inner product, and you can start canceling things out. If H is prime is identity, so if you don't do anything with output, which also makes sense if you, for example, think of just doing some pre-processing, you typically do it on the input space, but you don't want to like necessarily change the values that they're mapped to, right? So if that's the identity, then for any parameters phi, there exists parameters phi hat such that this holds, and such that there are equality, so the spaces are the same basically. But the probability and the most important part is that the probability measure P of the parameters is invariant on the H. So if you put all this together, is that you will get basically the same same spaces and the same sort of behavior, depending a little bit, of course. Like when you sample, obviously you will get different, but if you sample with the same, if you get like if you if you were to sample from 2 different computers or something like this, it would be the same sort of, if that makes sense. Yeah. So, but what if X differs? Well, we have some problematic spaces. I'll just run through this quickly. Obviously, if you have a single point, we cannot approximate anything really. It just goes, yeah, south. And if you consider the sphere as the input space, and only points on the sphere, not inside, so it's not a ball, but it's a sphere actually, together with tanh as activation function, you also get problems, because then whatever 2 points you construct the weights with, then if you look at 2 other points on the sphere, and like where the points are opposite of each other through the through 0 basically, these 2 points will have this, always have the same output in the for that neuron, except for the sign. So you cannot break this symmetry basically, which obviously constrict these functions that we can approximate. This can be fixed quite quickly with just adding a little bit more noise to it, but yeah, or changing the activation function. But these are as part like input spaces that we know doesn't work, like theoretically. So, but when this space is not single point, is 2 points, we can represent any function. So that means that just shows that it's really hard to like show what are necessary conditions on X. When it's 2, we can. When it's 1 point, we cannot. And of course, if you take the span of like the input space and close it, and it's input space again, so basically like if it's like a subspace, vector subspace, we don't have any issue with the direction, and real networks works great. And this also highlights that then we're still using the information about the dimensionality. So this could still be lower dimensionality in terms of compared to the ambient space. So if this thing here, for example, occurs, that it's much less than the dimension of the ambient space, our results still work, and you're still sampling from this very small, low-dimensional sampling space. But the theorem still holds, because you can basically figure out why just by looking at the orthogonal decomposition of some vector in the ambient space. Okay, so let's get to the empirical, which I'm sure a lot of people would like to see. So if we consider this function here, which is a barren function, in particular, it's a barren function that has the same norm regardless of the dimension. So it should be pretty good, and also barren functions are typically, or at least these kind of is very much, it should be very good towards like any extreme learning machine functions. So it's like both our models should do pretty good for both the one where we sample with the points, but also if we just sample arbitrarily. But what you can see is that yes, it works for L equals 1 for the random feature models. But if you do sampling, it works also when it goes deep, but it does not work for random features when it goes deep. It just struggles. And you see the reference lines is just with the in terms of the theorem that we showed. Yeah, here we see that's also for a random feature. It starts to struggle a little bit more, a little bit slower in convergence when the dimension goes up a little bit. While for any layers on R, it works still pretty well. We also looked at some classification problems from an OpenML benchmark scenario. We solved both through Adam and using just our sampling, and then solving the linear problem at the end. So we have 500 nodes, and then we tried with an optimized for 1 to 5 layers, hidden layers, to see which one was best, and then chose the best one for each Adam and sampling. For Adam, we also use some early sampling, and we also use some regularization for sampling. And obviously, the fit time is very, very different. The accuracy is quite similar. Sometimes sampling beats Adam, sometimes Adam beats sampling. And the important part, and an interesting part, I would say, is that the layer difference. So sometimes Adam would like had the best its best performance with, for example, 2 more layers than what we had. But it still occurred for sampling that we needed more layers to perform better or as good as Adam, while Adam needed fewer to get optimal performance. So these also show that it's useful to go deep when sampling as well. And also for like a fine-tuning situation. So we basically originally we had some very famous architectures that were originally trained on ImageNet, and then looking to classify cipher from this by just adding one hidden layer networks at the end and training them first, and then also doing fine-tuning, which is first training the one hidden layer for itself, freezing the original networks, and then also do some at the end we do some training overall with Adam for both the sampling and for like when we do Adam on the whole thing. We use some overstopping and some this learning rate here, which batch 32. And what we see is that adding a little more width to our sample networks, it's starting to surpass Adam in terms of when we keep like the original ResNet or VGG or whatever frozen, we do get better results. But it's not as important for us that they are better, because you can always think of, okay, can we optimize this more, this, but it's more that yes, we can get pretty good results and sometimes comparable to Adam, and not just compared to like random sampling from Gaussian, for example. You also see that's more stable in terms of like the if you look at the variance of the results, so the error bars here, they're definitely more stable when we sample. So this stripey here is when we also do some fine tuning, and then both rises quite heavily, of course. But sampling seems to be also a good starting point for fine tuning. This is also like the time what it says is basically that's obviously the really high factor or really high performance issue for our case is not the width in terms of like sampling, but it's this width of the last layer. It really depends on really depends on or makes the computational time much higher, right? So if you have high width, it's basically solving the linear problem. But this is also to take into account that these are GPUs trained, the orange ones, the Adam ones, and the blues are trained on CPUs. So take that in account as well. Now for just finishing up, looking at trying to connect it a little bit to your guys' field, and looking into like CNNs and these kind of things. We are looking into convolution now. It's definitely more tricky because what you could of course think of like having an image, choose patches, and then taking the difference between these two patches from different images, for example, and construct a kernel from this. But you do want them to share information, right? So you do want like you don't want to just use one part of the image to really enforce like this kernel. You would like to also allow different patches to inform the kernel. So yes, if you do this straightforward way, we're just taking two patches randomly. It obviously works well with like on like binary images like digits and these kind of things, but that makes sense, and it's very weak. But if you go to like higher things like cipher and stuff, it doesn't work. So that's what we're working on. We're also thinking about going how to fix a certain deep problem. Like even though we have some theory, and we can show that sometimes these sampling deep networks work well, they also can work pretty poorly. But we do think we have found some results here where we do some, we add some greedy optimization to it, not really enforcing higher computation time, not by much at least, but it allows us to go deeper and get better results. Obviously, you could also, of course, think of like MLP mixes and pointwise MLPs, and I'm sure you know much more about these kind of things than me, but obviously these use fully connected neural networks, so you can definitely try it out there. We have tried a little bit on pointwise MLPs. If you have very, very high width and one hidden layer, it works well, but there's definitely a lot more work to do there. Oh, it should not say visual intelligence. It's not visual intelligence, seems harder, even though it is harder. But what I was thinking more of is transformers. Transformers seems harder to do right now. Perhaps one can avoid attention, right? You have like these hyena operators and these kind of things where maybe we could avoid attention through that if we solve the convolution first. But yeah, this is definitely like the CNNs and stuff are things we are like working slowly towards right now. But the transformer part would be very is more in the realm of we don't know. Also for interpretability, for those people that work with this, you could definitely think of using these kind of things to get more interpretability. If you look at, for example, what neurons contribute to certain values, maybe some similarity measures, and then you can think of, okay, and then you can look at like what points are used for this, and then you can look at, okay, what are these points in the data set, and how can we connect that to interpret the results better. You could also think about like sampling many times and solving linear many times, and then see, okay, the points that are contributing a lot. For example, if you prune and after you pruned, for example, with just L1 regularization, after you pruned, you get rid of a lot of neurons. You can see, okay, which points are often included, and start to make sense out of that. Okay, so finally, there's a lot of things to do here. We just dipped our toes basically. Approximation results for sampling, both both for the just considering the whole input space and also finite training sets. This is something that we are working on or writing a paper on right now, using a lot of results and theory from the world of random feature methods. It's also random feature method and also like linear solver and least square results, of course. Understanding limitation and necessary requirements on the input space is also something that would be nice. I'll show you that it's not straightforward. Definitely a better view or framework of what happens when going deep. In terms of theory, it's quite hard to like work with, because once you sample, it's so many possible ways to sample like the L-1 layers. Also, the sampling space looks so much different depending on what you did in the previous layers when you constructed it. It's very hard to like work with theoretically right now, and that would be nice. Definitely maybe some regularization of distribution as well, and not just a regularization on the when solving the linear layer. Could be nice, especially if you have a lot of data. You could think of some dampening or something like this. And also you could think of like this is a very naive way with just taking the difference between two points. Maybe there are more ways to construct the weights that are a little bit more complex, but also expands the performance. And definitely this is the huge part, and this is we're working on, as I said, with CNNs, but definition transformers would be like very, very nice. But yeah, it's definitely difficult. And then also in terms of interpretability, but as I already mentioned, study which points are often chosen. But also I would highlight that we also think, and we have some students working on this as a student project, use as a tool to understand gradient optimization better. So try to map from, since we know how to map from a neural network through the proof that we've already done, from an arbitrary neural network to like a sample neural network, maybe we can use this to then run through optimization and like for each epoch, for example, map to our network and see how the points that are chosen changes. For example, this is something we're working on as well. And with that, I would say thank you, and yeah.